Velocity. This is Physics 2211. My name is Laura Weil. The purpose of this lab is to compare the position of an object traveling in the x direction with a constant velocity as is determined by observation compared to mathematical prediction. First, predicted location is found by the use of flow script, while the observed prediction is determined by inputting a video of the marker's motion into tracker. Principles being demonstrated are Newton's first and second laws, first of which states that an object must be acted upon by an external force in order for the movement to change. And the second represents the force equaling mass times acceleration. You can also see that the following assumptions were made throughout the course of the experiment. First, that air existence is negligible, friction from the surface of the table is negligible, finally, that there is no motion by the system in the y or z directions. You can also see later results from the experiment. Newton's first and second laws are primarily used throughout the course of the experiment. The first equation seen on the left is Newton's second law, which shows the difference in momentum and the difference in time, representing mass times acceleration. The second is the velocity update formula, and the third is the position update formula, which show how the ball moves over time. The procedure is this. The first step is using the video in the tracker. The video of the marker is taken and uploaded to tracker, in which case the mass of the system is selected frame by frame in order to observe the resulting graphs representing the x position over time. Flow script is then used by taking the initial velocity, mass, and a few other constants in order to determine a model for the x position of the system over time. These are then compared graphically, in which case everything is put into an Excel file where you can compare the two results as seen on the previous slide. First, you can see the observed or recorded data. The video below was from the tracker as seen above, in which case you can see the graph representing the x-axis, which in this case has a negative slope due to the negative and positive axes being flipped. The computational code model and its analysis were used by giving the initial position and velocity and change in time as the same as the observed model on the previous slide, although you can see that the final position and total time have slight variations, in this case being slightly larger or longer than the previous slide, causing some variation between the two. The final predicted versus observed x position of the system can be seen below. As you can see, the predicted or blue line is very linear and shows a constant velocity throughout the course of the system. The observed or orange line has slight variations, which show that or imply that there are certain external forces acting on the system that aren't being taken into account. Possible sources of error include external forces. These include forces such as friction by the table or air resistance that are not, in fact, negligible as assumed by the experiment. Tracker data is also a second source of error. In this case, the center of mass for the system could have been inconsistently marked when moving frame by frame in the system, creating an x position change that is inconsistent to the actual data. Data specifics, such as rounding, could have also not been taken into account or used properly. Rounding too early or too late, even inconsistently, could have caused errors in the data. How would the results change or stay the same if the axes were flipped? For example, if the positive and negative x-axes were interchanged. This can be seen when referring back to my tracker data, in which case the negative and positive x-axes are interchanged. This is fixed by simply flipping either the time or position data columns. The value of the data itself remains the same, although the slope of the x position graph will appear to have a negative slope. The computational model can predict the position of the system based on a net force of 0 newtons. Can this be used to determine how many pushes and pulls or forces are acting on the system to create this net force? While technically this can be determined, it will be very difficult because although the net force is assumed to be 0, many other forces would need to be understood in order to know how many pushes and pulls are truly acting on the system. In reality, the coded model is inaccurate in regards to the actual position of the system, meaning that there were more than likely external forces causing the net force to be greater than 0 newtons. Conclusions. The x position of the system in motion was observed as both an experimental and computational model, utilizing Newton's first and second laws. Although similar, the predicted and observed progressions of the x position of the system were not completely identical, implying that there is actually some form of external force acting on the system that must be accounted for. Thank you.